After introducing polynomials in our last video, we focused most of our discussion on end behavior. In other words, what happened at the ends of our function. What happened as we took x all the way to infinity, or what happened to our function as we took x to negative infinity. In other words, as we looked all the way right or all the way left. In today's video, we're going to talk a little bit more about what happens in the middle. In particular, what happens at the x-intercepts. Now, in context of polynomials, we also often call these zeros or roots, and so we'll define this a little bit more formally, as well as discuss some other nuances like multiplicity. But before that, let's take a quick recap of what we know of x-intercepts already. For the graph of a function on a Cartesian coordinate plane, where we label the horizontal axes the x and the vertical axes the y, or usually representing f of x if we're talking about functions specifically, the x-intercept is the point here where that function intersects with the x-axis. And this is something we can recognize visually on the graph, but also something that we can learn from the equation by identifying when that equation is equal to 0. In other words, this occurs when y is equal to 0. Or again, when f of x equals 0, when we're talking specifically about functions. And that same thing is going to be true for polynomials, and is also why we often will refer to them as zeros in this particular case, because they are when the function itself is equal to 0. And so formally, we can say that these zeros of a polynomial, p of x, which are also often referred to as roots or solutions, are the values of x, for which p of x is equal to 0, And again, these are the values that on a graph we see as the x-intercepts. And so for example, if we had a function f of x that looks something like this, we can identify two x-intercepts, one at -1 and one at +2. And these two values would represent our zeros. Now, beyond just recognizing these as the intercepts on a graph, we can also find the zeros given an equation of a function by solving for when that equation is equal to 0. So when we say find the zeros of f of x equal to x cubed plus 2x squared minus x minus 2, what we're really asking for is when does f of x equal 0? What values of x can we plug into this equation to get 0 as our output? And so to do that here, to answer those types of questions, we want to solve this equation. And so we'll solve for when x cubed plus 2x squared minus x minus 2 is equal to 0. And to solve many of these, we'll have to discuss some new techniques in later videos, but some of them we can utilize skills and tools that we're already familiar with from an algebra class to solve, like in this case here. To solve some polynomial functions, first we can utilize the zero factor property, which tells us that if we can write our expression into a factored form, in other words, a product of different factors like arbitrary a and b here, and all of that is equal to 0, then we must have either a equal to 0 or b equal to 0. In other words, if we can factor this expression, it's going to allow us to solve for what values of x make the whole expression equal to 0. And further, to factor certain expressions like this, where in particular there's 4 terms, we can utilize a technique known as factoring by grouping. And this might sound really fancy, but all it really means is to look at the different terms across our polynomial, across our expression, and figure out which ones have common factors with each other and group them appropriately. So for instance, we might look at 2x squared and minus 2 and realize that they share a factor of 2, and so it's going to be worth pairing those together. Similarly, we might look at x cubed and x and realize that those have a common factor of x, and so we'll group those together when we begin to factor. And so what will that look like? Well, we'll take x cubed plus 2x minus x minus 2, and first we'll just rearrange that. So we have our groups written together. And so we'll write x cubed minus x plus 2x squared minus 2 equal to 0. And then looking at our first group, x cubed minus x, we know both of those terms share a common x, and so we'll factor that out, leaving us with x cubed over x, or x squared, and minus x over x, or minus 1. Similarly, looking at our second group here, we know that these both share a common factor of 2, and so we'll factor out that 2, leaving also an x squared minus 1. Now that we've factored those groups, we can recognize that this term here, this product and this product, both share a factor of x squared minus 1, and so we can factor that out further from our expression, giving us x squared minus 1 times what remains here, which is x, plus what remains here, which is 2. And so we have the quantity x squared minus 1 times the quantity x plus 2. Then by our zero factor property, we can recognize that if this whole expression is equal to 0, then either of these two factors would have to equal 0. And so we can solve those individually. So this will give us that either x squared minus 1 would have to equal 0, or x plus 2 would have to equal 0. And we can solve these accordingly. For instance, here we might add 1 to both sides, giving us x squared is equal to 1, and then taking the square root of both sides, we know that x is equal to plus or minus 1. And then looking on our other hand, we have minus 2 from both sides, giving us x is equal to negative 2. And so this gives us now 3 solutions, or 3 zeros. And we can check any of these answers by plugging them back into our original equation and verifying and confirming that this will in fact give us a result of 0. So for instance, if we take negative 2, that will be negative 2 cubed plus 2 times negative 2 squared minus negative 2 minus 2. And for this to be a root, for this to be a 0, this computation has to add up to 0. And so negative 2 cubed gives us negative 8. Negative 2 squared is going to give us positive 4. And then minus negative 2 becomes plus 2. And then we just carry down the minus 2. We can do some quick cancellation and quick simplification here when we take the product of 2 and 4, which gives us 8, and then 2 minus 2, which will cancel to give us 0, leaving us just to cancel the negative 8 and positive 8, which of course also sum to 0. And so we can confirm that negative 2 is a root of this function. And so we can say, therefore, the zeros of f are negative 2, negative 1, and 1. Now, one thing that's worth noting is that we have 3 solutions here, 3 zeros, and our degree of our polynomial, in other words, the highest exponent, is also 3, and that's not a coincidence. In fact, in particular, because there is a root that corresponds with every factor, and that exponent is going to tell us how many factors we have of our equation, the degree will also tell us the largest number of roots that we can have. In other words, we can note that a polynomial of degree n has at most n roots. And that at most piece is key because although in that last example we had 3 roots for a degree 3 polynomial, we'll see in this example that this might not always be the case. And so let's see if we can find the zeros for g of x equal to x minus 2, the quantity squared, times x plus 3 times x minus 3. Once again here, we're going to solve for when g of x is equal to 0. In other words, we need to solve for when x minus 2 squared times x plus 3 times x minus 3 is equal to 0. And we can again utilize the zero factor property to do this. In other words, for this whole expression to be 0, at least one of these 3 factors would have to be. And so we can then solve for x minus 2 squared is equal to 0, or for when x plus 3 is equal to 0, or for when x minus 3 is equal to 0. And so if we start here on the left, we can begin by taking the square root of both sides. In this case, that's just 0, so we don't have to worry about the plus or minus since 0 is not positive or negative. And so we'll have x minus 2 equal to 0. We can add 2 to both sides, giving us x is equal to 2. We can look in the middle here and subtract 3 from both sides, giving us x is equal to negative 3. Or look on the right here by adding 3 to both sides, giving us x is equal to positive 3. And so we could say, therefore, the function g, has roots negative 3, 2, and 3. And we'll notice here that this has 3 roots, even though if we were to determine the degree and multiply x squared times x, we would get x to the 4th, and so have a degree 4. And so we can have a case where we have fewer roots than the degree, but we can't ever have a case where we have more roots than the degree. But this does bring us to something interesting, because the behavior of this root at x is equal to 2, right, where we have this square factor, is going to be a little bit different than the behavior when we have a factor like x plus 3 or x minus 3. And to see that best, we'll want to take a look at the graph. And so here we have the graph of x minus 2, the quantity squared, times x plus 3 times x minus 3. And we'll see right on this graph, we have each of those roots at 3, 2, and negative 3. But if we look closer, we'll notice a distinction between what happens at negative 3 and 3 versus what happens at 2. Right, at negative 3, we start above the axes and we cross below the axes. At positive 3, we start below the axes and cross above the axes. But at 2, we start below the axes, we come up to 0 and touch the axes, but then still stay below the axes. And that distinction is going to be dependent on what's called the multiplicity of the factor for that root. More specifically, we can say that for a polynomial p of x and a factor x minus r that occurs k times, that occurs exactly k times, r is called a zero or root with multiplicity of k. In other words, the multiplicity of a root is just the number of times its corresponding factor is being multiplied. So for example, with our last function g of x, we had x minus 2 squared times x plus 3 times x minus 3. Here the root of positive 2 coming from this factor is being multiplied twice, right? Because we have it squared, that's multiplied x minus 2 times x minus 2. Since it's being multiplied twice, we would say this root 2 has a multiplicity of 2. Likewise, each of these roots here, positive 3 and negative 3, have a multiplicity of 1. So the root of negative 3 has a multiplicity of 1. And likewise, the root of positive 3 also has a multiplicity of 1. And another way to think of this is that the exponent of the factor in the expression, assuming that they're all combined, is the multiplicity of that root. And now the reason why this is significant, at least in terms of looking at a graph of a polynomial, is because the parity of the multiplicity, in other words, whether or not it's even, like in the case of x minus 2 squared, or odd, like in the case of x plus 3 to the first, that's going to determine whether the graph goes through the x-axis or whether it just touches and turns back. And so what we'll find is that the graph of a polynomial will touch the x-axis and turn when the multiplicity of a 0 is even, and will cross the x-axis when the multiplicity of a 0 is odd. And that is in fact what we saw with this graph here. At negative 3, where we had an odd multiplicity, right? This is raised to the power of 1. We crossed through the x-axis. At positive 3, where the corresponding root x minus 3 also has an odd power of 1, we see this graph cross through the x-axis here. But then at our root of positive 2, where our corresponding factor is raised to the second power, an even power, we can see that as we zoom in, we watch this graph go up to the x-axis, touch, and then turn back around. And so that distinction is determined based on whether or not the multiplicity is even or odd. I hope you found this video helpful. Hopefully now we're starting to get a sense not only of what happens at the ends of our graphs with polynomials, but what can also happen at the middle as we touch and cross or touch and turn back at the x-intercepts, or as we now know them, at the zeros. And as we start to put together all of this information, we can look forward to, in the next few videos, to graphing these polynomials and finding a little bit more about the specifics and nuances. But thanks for watching. As always, if there is anything that I can do to help, or if you have any questions, please reach out. Otherwise, I hope you have a great rest of your day.